Imagine you control the world's most advanced factory. You can build the impossible. The chips that power our artificial intelligence, our smartphones, our very future. They all come from your machines. You are the undisputed king of technology. Now, what if I told you that at any moment, someone you barely think about could flip a switch and turn your entire empire to dust? For decades, the world has been mesmerized by the rise of Taiwan's TSMC and South Korea's Samsung and SK Hynix. They are the titans of the semiconductor industry, the public faces of our digital age. Their foundries, sprawling, sterile complexes where robots dance in a ballet of atomic precision, are geopolitical flashpoints, their every move watched by world leaders. South Korea, for its part, is a memory chip juggernaut. Samsung and SK Hynix together command over 73% of the global market for DRAM, the volatile memory that acts as the short-term brain for our computers and phones, and over 51% of the market for NAND flash, the long-term storage that holds our photos, apps, and operating systems. They are, in every sense, the bedrock of the digital economy. Taiwan, in particular, has built what it calls a silicon shield, the idea that its dominance in chip manufacturing, producing a staggering 90% of the world's most advanced logic chips, makes it too important to fail, too critical for the global economy to allow a hostile takeover. This technological supremacy is seen as a deterrent, a guarantee of security in a volatile world. The theory is simple. If the world needs your chips to function, the world will protect you. It's a powerful and compelling narrative, one that has shaped global strategy for years. But in the summer of 2019, a quiet political dispute between Tokyo and Seoul sent a shockwave through this ecosystem. It revealed a hidden dependency, a foundational choke point so critical yet so invisible that it forces us to ask a terrifying question. Who really controls the chip industry? The public and political focus is almost entirely on the fabrication stage, the foundries themselves, but this is a strategic blind spot. The true, less visible leverage lies further upstream, in the hyper-specialized world of chemical engineering and material science. The answer, it turns out, is not in Taiwan or South Korea. It's in a handful of unassuming chemical plants in Japan. The crisis began not with a bang, but with a court ruling. In late 2018, South Korea's Supreme Court ordered Japanese companies, including Mitsubishi Heavy Industries and Nippon Steel, to compensate victims of forced labor during Japan's colonial rule. For Seoul, this was a matter of justice for individuals, a right that couldn't be signed away by governments. For Tokyo, which insisted all claims were settled by a 1965 treaty that normalized relations, this was an unacceptable breach of an international agreement. Japan was furious, but its response wasn't just diplomatic outrage, it was brutally strategic. On July 1, 2019, Tokyo announced it was tightening export controls on 3 seemingly obscure chemicals destined for South Korea. The first was fluorinated polyimides, a critical component for the flexible OLED displays in the latest smartphones. The second was photoresists, a light-sensitive liquid essential for photolithography, the process of printing microscopic circuit patterns onto chips. The third was ultra-high purity hydrogen fluoride, a gas used for cleaning and etching silicon wafers at the atomic level. To the outside world, it looked like bureaucratic red tape. Instead of a simple bulk license, Japanese exporters would now need to apply for an individual license for every single shipment, a process that could take up to 90 days. But to the executives at Samsung and SK Hynix, it was a declaration of war. Why? Because their multi-hundred-billion-dollar empires were almost completely dependent on Japan for these materials. The numbers were stark. According to the Korea International Trade Association, South Korea imported 94% of its fluorinated polyimides from Japan. For photoresists, the dependency was 92%. And while the figure for hydrogen fluoride was a lower 44%, for the ultra-high purity grades required for the most advanced chips, The reliance was effectively 100%. Japan had chosen its weapons with surgical precision, targeting the exact inputs where Korea had no immediate alternative. This wasn't just a trade dispute. This was a live-fire exercise in economic statecraft. Japan was demonstrating its chokehold power, weaponizing the deep structural interdependencies of the global supply chain. The Japanese government's official justification cited national security concerns and alleged mismanagement of sensitive materials by Seoul. But this was widely seen as a pretext. Prime Minister Shinzo Abe himself linked the move to the forced labor issue, stating that because South Korea was failing to abide by international agreements, Tokyo had to assume it was also breaking rules on sensitive exports. The timing, immediately following the court ruling, and the precise targeting of choke point items pointed to a different motive: leverage. The effect was immediate. Panic erupted in Seoul. Samsung's de facto leader, Vice Chairman Lee Jae-yong, flew to Tokyo on an emergency mission to meet with suppliers and plead for shipments. The CEO of SK Hynix did the same. They sent urgent notices to their partner companies, telling them to stockpile 90 or more days' worth of any and all Japanese materials they could get their hands on. The data tells the story of the exercise's success. Japanese exports of hydrogen fluoride to South Korea plummeted by an astonishing 87.9%, almost overnight. The shockwaves rippled across the globe. Major US tech companies like Apple, Amazon, and Google, who rely on Samsung and SK Hynix for the memory chips that power everything from the iPhone to their massive data centers, began making frantic calls to Seoul. They wanted to know if the global supply of DRAM and NAND flash memory was about to be cut off. In Taiwan, TSMC's co-CEO rated the dispute as the biggest uncertainty for the industry, fearing a collapse in orders if its clients couldn't get the memory chips they needed. The conflict rattled global stock markets, with South Korea's KOSPI index hitting a 7-month low and the tech-heavy KOSDAQ plunging over 7%, triggering a trading halt for the first time in years. This was a calculated move, targeting the precise materials where South Korea was most vulnerable. It was a chilling demonstration that Japan could, at will, threaten to shut down the crown jewels of the Korean economy. This event permanently altered the risk calculation for both Seoul and Taipei. It forced them to view their Japanese suppliers not just as partners, but as a potential strategic vulnerability. Japan, feeling its decades-long dominance in finished electronics fade, had fired a warning shot, reminding the world, and especially its ambitious neighbors, where the foundational power still resided. So why is this dependency so absolute? Why can't a technological giant like Samsung, with its vast R&D budget and army of engineers, just make these chemicals itself? The answer lies in a world of near-impossible physics and chemistry, a realm that is less about industrial scale and more about a kind of technological black magic, perfected over decades of painstaking, incremental improvement. It all starts with this: a perfect, shimmering disk of silicon, a silicon wafer. It is the canvas upon which every microchip is painted, and over 60% of the entire global market for these foundational disks is controlled by just 2 Japanese companies, Shin-Etsu Chemical and Sumco. In fact, when combined with other Japanese firms, they control about half of the entire market for all semiconductor materials. Making a wafer is an art form, a process that pushes the boundaries of material science. It begins with melting highly purified polycrystalline silicon in a quartz crucible at a blistering 1,425 degrees Celsius. Then, a tiny, perfectly oriented seed crystal is dipped into the molten silicon. This seed is then pulled upwards, excruciatingly slowly, just a few centimeters per hour, while both the seed and the crucible rotate in opposite directions. This is the Czochralski method, or CZ method, invented in 1916. The goal is to grow a massive, single crystal ingot, sometimes 2 meters long and weighing several hundred kilograms, that is atomically perfect. The entire process takes place in a stable, vibration-free environment under an inert argon atmosphere. Any microscopic impurity from the crucible, any unwanted vibration, any minute temperature fluctuation can introduce defects into the crystal lattice, ruining the entire multi-million-dollar batch. But the true challenge, the black magic that separates the masters from the apprentices, is achieving purity. We're not talking about 99% pure. We're talking about 11 nines purity, 99.99% pure silicon. That's an impurity level of 1 part per trillion. It's the equivalent of finding a single contaminated grain of sand on a beach a kilometer long. This isn't just about filtering. It's about decades of accumulated tacit knowledge, what the Japanese call monozukuri, the art, science, and craft of making things. It's an intuitive understanding of how to control thermal gradients, pull rates, atmospheric pressures, and dopant concentrations. It is a process so complex and sensitive that other nations have poured billions of dollars into replicating it, and have largely failed to match the quality and consistency of the Japanese masters. If the silicon wafer is the canvas, photoresist is the magic paint. And in the world of cutting-edge chips, the master artists are Japanese. Companies like JSR Corporation, Tokyo Oka Kogyo, and Shin-Etsu Chemical dominate the market for the most advanced photoresists. Their control is especially absolute in the most critical segment: photoresists for extreme ultraviolet, or EUV, lithography. EUV lithography is the technology that allows chip makers like TSMC and Samsung to build today's most advanced chips. It uses light with an incredibly short wavelength of just 13.5 nanometers to print impossibly small circuits. But this light is a diva. It is absorbed by almost everything, including air and even glass lenses. Therefore, the entire multi-hundred-million-dollar machine must operate in a near-perfect vacuum, using a complex system of ultra-reflective mirrors to guide the light onto the wafer. The photoresist itself is a hyper-complex chemical cocktail. When a single high-energy EUV photon strikes the resist, it must trigger a precise chemical reaction. Typically, it activates a photoacid generator, PAG, which releases an acid that then alters the solubility of the surrounding polymer, allowing it to be washed away to leave a perfect nanometer-scale circuit pattern. But here's the impossible trade-off: a fundamental problem in lithography known as the RLS triangle: resolution, line-edge roughness, and sensitivity. If you make the resist more sensitive to react to fewer expensive photons, increasing throughput, the statistical randomness of those photons, the shot noise, causes the edges of your circuit lines to become rough, leading to defects and short circuits. If you formulate the resist to create smoother lines and improve resolution, you typically need a higher dose of photons, which reduces sensitivity and slows down the entire factory. Solving this trilemma is the holy grail of lithography. It's not a matter of simple reverse engineering. It is a black art of chemical formulation, balancing polymers, PAGs, quenchers, and solvents in a delicate dance. Japanese firms, through decades of R&D, hold a near monopoly on these secret recipes, with companies like TOC, JSR, and Shin-Etsu commanding a combined 90% of the critical EUV photoresist market. The barrier to entry here is not primarily financial, it's intellectual and temporal. You simply cannot buy 40 years of incremental trial-and-error chemical research. This explains why the dependency on Japan is so profound and so difficult to break. This brings us to the ultimate paradox. Taiwan Semiconductor Manufacturing Company, or TSMC, is arguably the most important company in the world. It fabricates over 60% of the world's semiconductors by revenue and over 90% of the most advanced chips below 10 nanometers. It has the money, the talent, and the political will of a nation behind it. So why hasn't it broken free from Japan's chemical empire? Why does the undisputed king of chips still bend the knee to its suppliers? The answer is that this isn't a weakness, it's a core part of its strategy. It is a calculated reliance. TSMC's entire business model, pioneered by its legendary founder Morris Chang, was to focus on one thing and do it better than anyone else on Earth: contract manufacturing. By outsourcing the chip design to fabless companies like Apple and Nvidia, and sourcing the absolute best materials from specialists in Japan, TSMC could pour all of its immense capital and engineering talent into perfecting the fabrication process itself. It's a deeply symbiotic relationship. Japanese material science enables TSMC's manufacturing prowess, and TSMC's massive, predictable orders for the latest and greatest materials fuel the R&D of its Japanese suppliers. This partnership is so crucial that TSMC has even begun collaborating directly with firms like Ajinomoto, famous for its MSG seasoning, to develop the next generation of insulation films needed for advanced AI chip packaging. But make no mistake, it is a fundamentally unequal partnership. While TSMC has immense bargaining power and can set prices, its power evaporates when it comes to the most critical inputs. It can, in theory, switch to a different supplier, but for the most advanced silicon wafers and EUV photoresists, there are no viable alternatives at the necessary scale and quality. In this specific domain, Japan holds the choke points. This unequal dynamic is perfectly illustrated by TSMC's recent massive investments in Kumamoto, on Japan's southern island of Kyushu. On the surface, this looks like TSMC expanding its empire to diversify production away from the geopolitical fault line of Taiwan. But look closer. This isn't just about diversification. It's about moving closer to the heart of its own supply chain. By building fabs in Japan, TSMC isn't just securing its access to chips, it's securing its access to the materials needed to make those chips. It's a move to de-risk its supply chain by placating its own masters. The Japanese government has rolled out the red carpet, pledging over yen 1 trillion, roughly $7 billion, in subsidies for TSMC's first 2 Kumamoto fabs. This is because the partnership reinforces Japan's own national strategy of strategic indispensability. The venture, known as JASM, Japan Advanced Semiconductor Manufacturing, is a joint project with TSMC's own key Japanese customers, Sony and Denso, who are now major stakeholders. This move embeds TSMC deeper into Japan's industrial ecosystem, making it even more reliant on Japanese suppliers. This is not an act of colonization by TSMC, but arguably one of strategic vassalization. By moving production to its supplier's territory, TSMC mitigates the risk of a supply cutoff, but in doing so, it deepens the very dependency it seeks to manage. This creates a powerful geopolitical alignment. Taiwan and Japan, both democratic nations facing threats from China, are intertwining their most critical industries. TSMC's reliance on Japan becomes a strategic asset for both. An attack on Taiwan that disrupts TSMC would now cripple Japan's chemical industry, giving Tokyo a powerful economic incentive to support Taiwan's defense and maintain regional stability. But this chemical empire is not invincible. Japan's throne is more fragile than it appears. Its greatest strength, its deep, geographically concentrated ecosystem of expertise, is also its greatest weakness. The country is a hotbed of natural disasters. Japan sits on the Pacific Ring of Fire, making it exceptionally vulnerable to earthquakes and tsunamis. A major seismic event in the right place could knock out a critical plant and send the entire global tech industry into a tailspin. The concentration of new facilities in Kumamoto, a region hit by a major earthquake in 2016, highlights this very real risk. Then there's the human element. Japan is facing a demographic crisis unlike any other developed nation. A plummeting birth rate, a rapidly aging population, and a persistent shortage of STEM graduates create a looming shortfall of the very engineers and technicians needed to maintain this technological edge. And finally, Japan itself is dependent. it must import the vast majority of the raw minerals and energy needed to create its chemical magic, making it vulnerable to its own set of supply chain disruptions further upstream. The 2019 trade dispute was a painful but necessary wake-up call for South Korea. In its wake, Seoul launched a massive, multi-hundred-billion-dollar national strategy to break its dependency on Japan. Dubbed the K-Semiconductor Strategy, its ambitious goal is to achieve 50% self-sufficiency in core materials, parts, and equipment by 2030, and against all odds, it has seen some stunning successes. In a matter of months, Korean chemical companies like Seoul Brain and SK Materials managed to develop and mass-produce the ultra-high purity hydrogen fluoride that Japan had cut off, a feat many industry experts thought would take years, if it was possible at all. The government expedited paperwork and provided funding, allowing firms like Seoul Brain to build new plants and ramp up production with incredible speed. But the hardest challenges remain. While they solved the hydrogen fluoride problem, localizing the complex black magic of EUV photoresists has proven far more difficult. The Korean Gambit has shown that the walls of Japan's empire can be breached, but taking the throne is another matter entirely. Japan's power is potent, but brittle. The very act of using its leverage, as it did in 2019, directly inspires and accelerates efforts by its targets to undermine that leverage. This creates a feedback loop where Japan's dominance is, in a way, self-eroding. Its power exists on a spectrum of difficulty. Some materials are replicable with a massive national effort, while others are not, at least not yet. This means the silent emperor rules best when their power is felt, but not seen. Lurking behind this intra-Asian rivalry is the immense shadow of China. Beijing is pouring hundreds of billions of dollars into its domestic semiconductor industry, aiming for complete self-sufficiency as part of its Made in China 2025 plan. While it lags years, perhaps decades, behind in both advanced fabrication and materials, its sheer scale, political will, and willingness to use any means necessary to acquire technology mean it cannot be ignored. A future where China masters these foundational technologies would not just disrupt the market, it would shatter the current world order. For years, the world's geopolitical attention has been fixed on the foundries of Taiwan, seeing them as the ultimate choke point in our technological world. Commentators and politicians warn that a conflict in the Taiwan Strait would bring the global economy to its knees by cutting off the supply of advanced chips. But we've been looking in the wrong place. The 2019 trade war and the quiet chemistry behind our chips reveal a deeper, more fundamental truth. The real power, the foundational control over the digital age, doesn't lie with those who assemble the final product. It lies with those who master the raw elements. It lies in the quiet, indispensable chemical empire of Japan. This understanding reframes the entire strategic landscape. Japan's decline in finished chips, a narrative of a fading giant since the 1980s, masked its strategic consolidation of power in the foundational materials and equipment that nobody else could master. The 2019 dispute was a chilling demonstration of how this material dominance can be used as a potent geopolitical weapon, a tool of economic statecraft that can hold entire industries hostage. And the competitive moat protecting this empire isn't built of concrete and steel, but of something far more formidable: knowledge. The black magic of achieving atomic-level purity is a fortress built on decades of accumulated wisdom, one that capital alone cannot easily storm. The silent war for the soul of the semiconductor is just beginning. The key battlegrounds to watch are not in the Taiwan Strait, but in the laboratories of Seoul, the industrial parks of Kumamoto, and the state-funded research centers in China. The race is on to either break or reinforce Japan's quiet chemical supremacy. The future of technology, and perhaps the global balance of power, may depend on who wins.